Welcome to this explainer. Okay, I want you to imagine a place so unbelievably cold that it makes the freezing, desolate surface of Pluto look like, well, a tropical vacation. We're not just talking about temperatures colder than Antarctica or even colder than the deepest, darkest void of empty space. No, we're talking about a place that is actually physically colder than the ancient, leftover heat from the Big Bang itself. Today, we're jumping right into this mystery. We're going to explore the mind-bending physics of extreme cold, bust a few incredibly stubborn Hollywood myths, and uncover a cosmic anomaly billions of kilometers away that just flat out breaks all the known rules of the universe. So, what exactly is the coldest place in the universe? To figure this out, we actually need to completely rethink what the word cold even means. It's not some physical substance you can hold in your hand or some invisible energy creeping into your living room. Temperature is really just a measurement of the physical motion of atoms. When atoms move fast, they generate heat. But when those same atoms start to slow down, that's when things get cold. Cold is literally just the slowing down of atomic motion. It's basically the universe slamming on the brakes. Let's step down the temperature scale for a second to really see this in action. Start right at the top with the fast-moving, super energetic atoms in your morning cup of hot coffee. As things cool off and drop down to room temperature, those atoms start to slow their frantic dance. Drop down to ice, and they get sluggish. By the time we hit extreme stuff like liquid nitrogen and then liquid helium, the atoms are barely vibrating at all. And then finally, we reach the absolute bottom tier near absolute zero, where atoms practically stop moving entirely. They're just locked into place. And that bottom tier brings us to a fundamental concept, absolute zero. At 0 Kelvin, which is a bitter negative 273.15 degrees Celsius, atomic motion comes to a complete grinding halt. The atoms lose their kinetic energy entirely. They just have nothing left to give. This is the ultimate, unbreakable floor of temperature. Nothing can naturally become colder than absolute zero because you simply can't go slower than a dead stop, right? But here's the wild twist. Even though deep space is incredibly vast and mostly empty, it isn't actually this cold. It turns out deep space sits at an average temperature of 2.7 Kelvin. See, because temperature only exists when particles exist, the near-empty vacuum of space still manages to hold on to this tiny residual bit of warmth. This constant 2.7 Kelvin acts as a strict minimum baseline temperature for the entire observable universe. Even if you were floating in the absolute deepest, darkest void between galaxies, you'd still be bathed in this microscopic warmth. But where exactly is that baseline heat coming from, if space is supposed to be, empty? Well, it's because empty space is never truly empty. It's completely saturated with a cosmic microwave background. Think of the universe as basically sitting in this vast, faint microwave bath left over from creation. This is literally the ancient glowing heat from the Big Bang itself, created 13.8 billion years ago. As the universe rapidly expanded out from that searing hot fireball, it cooled down, sure, but that ancient primordial light, it still exists everywhere around us. Meaning, any object naturally exposed to deep space is eventually going to warm up to this 2.7 Kelvin background temperature. So, in theory, nothing natural could ever be colder than this ancient cosmic glow. Which brings us to the impossible anomaly, discovering the Boomerang Nebula. For decades, scientists thought this 2.7 Kelvin rule was absolutely unbreakable. That is, until the 1980s, when they pointed their telescopes toward the Centaurus constellation and found something that simply shouldn't exist. Located about 5,000 light-years away, they discovered the Boomerang Nebula. This is a dying star that just completely floored the scientific community. It's this bizarre, swirling cloud of illuminated gas created by a star in its final death throes, and it's rightfully earned the nickname the refrigerator of the universe. Later on, it was photographed in this haunting, gorgeous detail by the Hubble Space Telescope, and it totally defied everything we thought we knew about the limits of extreme cold. When astronomers actually managed to measure the temperature of this swirling nebula, they were absolutely baffled. They found it sitting at a seemingly impossible 1 Kelvin. That is, negative 272 degrees Celsius. Just think about the sheer impossibility of that for a second. It was physically colder than the 13.8 billion-year-old leftover heat from the Big Bang, literally colder than the empty space surrounding it. So how exactly can a dying star be colder than the Big Bang itself? That's the million-dollar question. How did this star pull off this impossible cosmic magic trick? If the entire vacuum of space is naturally warmed to 2.7 Kelvin by that ancient afterglow, How on earth did the Boomerang Nebula push its own temperature down to a freezing 1 Kelvin? Like, what mechanism could possibly fight back against the baseline heat of the entire universe? To understand this brilliantly simple mechanism, we can actually compare this dying star, which, by the way, is violently ejecting gas at over 500,000 kilometers per hour, to a common everyday object, a can of spray deodorant. Seriously, they are doing the exact same thing. When you press down and spray a can of deodorant, the compressed gas expands rapidly outward, and that metal can instantly feels freezing cold in your hand. The dying star is mimicking this exact same cooling physics, just on a massively scaled-up galactic level. This happens through a physics principle called adiabatic expansion. As the gas from the dying star is ejected, it expands outward incredibly aggressively into the vacuum of space. But expanding like that, it takes a massive amount of work. The gas has to burn through its own internal energy just to push its particles away from each other at such a rapid speed. And in physics, when a gas loses its internal energy, it loses its heat. Because the gas in this nebula is expanding so incredibly fast, it plummets way below the background temperature of the universe itself, creating this literal natural cosmic refrigerator. Let's look at the human element and surviving the nebula. It's time for a fascinating thought experiment. What would actually happen if you somehow found yourself floating inside the Boomerang Nebula, completely unprojected? First off, we absolutely have to bust that classic Hollywood myth of a person instantly freezing solid and snapping like an icicle the second they hit space. That just wouldn't happen, not even at 1 Kelvin. Because space is a vacuum with zero pressure, the water inside your human tissues would actually begin to rapidly boil and then slowly evaporate. You'd essentially turn into a rather unpleasant cosmic freeze-dried snack. And while that gruesome process is happening, you'd also be getting hit with severe, unfiltered stellar radiation. But ultimately, death would actually come from a remarkably mundane lack of oxygen, long before that mind-numbing cold of 1 Kelvin ever had the chance to turn you into a block of ice. Which brings us to breaking limits with artificial extreme cold. While the Boomerang Nebula holds the record for the coldest natural place in existence, human beings are incredibly resourceful and, let's be honest, slightly obsessive. We've actually engineered even colder environments right here in our own domain to unlock completely new hidden realms of physics. Scientists are using some truly wild techniques like magnetic traps, quantum cooling, and especially laser cooling. Now, using lasers to cool something down sounds completely backward, right? We usually associate lasers with burning heat. But in these setups, scientists use precisely tuned lasers to essentially play atomic bumper cars. They fire photons that perfectly oppose the direction an atom is moving, gently striking it over and over to slow its momentum down to a crawl. Through these incredible methods, research labs at MIT, Harvard, and NASA's Cold Atom Lab aboard the ISS have managed to cool atoms down to just a billionth of a single Kelvin. Inside that cold atom lab, scientists have reached an absolutely absurd, record-breaking temperature of 100 picokelvin. That is 0.00000001 Kelvin. It is entirely artificial, painstakingly crafted inside a high-tech vacuum chamber, but it sits just a microscopic fraction of a hair above absolute zero. It is so unbelievably cold that it actually makes the 1 Kelvin of the Boomerang Nebula look almost pleasantly warm by comparison. So why go through all this trouble? Well, because at this extreme level of artificial cold, the standard, everyday rules of reality just warp completely. As atoms slow down this dramatically, the hidden world of quantum mechanics suddenly becomes visible to the naked eye. Matter stops behaving like tiny solid spheres and literally begins acting like smeared-out quantum waves. We see perfect superconductivity appear with zero electrical resistance, and things get spectacularly weird. Like superfluid helium loses all friction, defies gravity, and will literally crawl its way up and over the walls of its container. No way, right? Accurately capturing these bizarre quantum states isn't just a fun party trick. It's absolutely vital for things like atomic timekeeping, advanced sensors, and the entire future of ultra-powerful quantum computers. If there is one central thing you take away from this explainer, let it be this. Extreme cold isn't just the simple absence of heat. It's an active, transformative state. When you lower temperature enough, it fundamentally alters the very building blocks of reality. It actively changes physics itself, dramatically shifting how matter behaves on a quantum level and revealing the hidden architecture of our universe. Our universe began 13.8 billion years ago as an unimaginably hot, chaotic fireball. Yet today, the gentle death of a single star has created the coldest natural place we've ever seen, and human curiosity has artificially pushed those limits even further into the impossible. As we continue to map out these extreme quantum states and impossible nebulas, it leaves us with one final, kind of haunting thought. What undiscovered cosmic structures, what exotic dark matter interactions, or even colder natural mysteries are still hiding out there in the dark, just waiting for us to find them?